Metamaterials, man-made magical things that can potentially create invisibility cloaks and superconductors, are making their way into every new innovation space. For my TKS Focus project, where I dive super deep into the working of a specific emerging technology aiming to create a scientific solution to a global problem, I furthered the possible uses of metamaterials in solar panels. Let's unpack that. Less than 0.000000005% of the sun's energy produced per second reaches the Earth, out of which our current solar PVs that use something called an ionic doped lattice to create a potential difference can't even store 10% on average. The culprit behind this is reflection. Solar cells are conventionally not designed to transmit 100% of incident light and convert it to electrical output due to something called diffuse reflection, which occurs as light quickly changes speed between mediums. And it's a form of energy dissipation that massively affects how much energy solar panels can efficiently convert to electricity. How do metamaterials have anything to do with this, though? Well, they have a unique property called negative refractive indices, which means they can bend light of different wavelengths in ways that normal optical sheets and films can't. They can be manufactured at the nanoscale, which allows them to be tailor-made to a multitude of frequencies. And that range of frequencies is extremely selective. In this stage of my project, I loaded a metamaterial surface array onto a wideband antenna to reduce radar cross-section and increase absorption of electromagnetic waves. That sounds like a bunch of words, but let's unpack what that really means. A wonderful research paper I used, written by scientists of the Institute of Engineering and Technology, showcased the applications of metamaterial subwavelength structures. Those are nothing but microscopic geometric alterations that can make a material change its absorptive capacity of light in super multidimensional ways. This research team was able to demonstrate with evidence an increased radiating performance of wideband antenna. You might be asking, what does this have to do with radar, though? According to my research, radar signature or radar cross-section is reduced in mediums where transmission is not narrow band. That means that the material can absorb and transmit signals that correspond to an extremely wide range of frequencies. For applications like military vehicles, where wideband signals should not be detectable on radar at all, because otherwise the position of the object is located, RCS is reduced. So this antenna is structured as a radiation patch that conducts energy, and it's fed by a wire that makes up the bulk of the antenna. You've seen antennas before, they're just long wires. And that's exactly what this is as well. Here is where metamaterials come in making this so much simpler than it is. I designed these unit cells with the intention of reducing RCS in the wideband frequency range such that they satisfy the condition that the phase difference of the incident waves is less than 180 degrees. When I first started doing my research, I didn't know what that meant. But basically, it means that light shouldn't be allowed to completely change phase or reflect when it bounces off a surface that has a higher refractive index than air, because that means that the state of anti-reflection has been reached. That means all of the light that's incoming to this metamaterial substrate has been absorbed. Each of these patches that I've designed have their own configurations. This square radiation patch, for example, and this Jerusalem cross radiation patch are both made of the same dielectric metamaterial, and they are equally symmetrical. When I put them together, they exhibit something called dual polarization, which means that they can receive signals in both the vertical and horizontal orientations. It took me weeks to calibrate one of these unit cells because of their properties. The research I was modeling it off of prescribed certain behaviors that I couldn't just randomly cook up out of thin air, such as the permittivity of the substrate, the thickness of the patches where they're supposed to be centered, and some other properties that were all precise measurements that could change my entire output, even if I altered them by 0.01 nanometers. In fact, these models are so tiny that they probably measure thinner than your fingernails. Before testing whether my simulation would actually reduce RCS when assembled in a grid, I tested their individual performances and I obtained some pretty fantastic results. In the case of the metamaterial cell that used a square radiation patch, this graph was observed when I plotted the frequency of the light ray against the angle of the reflection phase. What we're looking for is the frequency at which this phase angle equals 0 degrees, because that means that the cell is not reflecting any light in the opposite direction, and that's a good thing, because it means that no signals are being given out of the antennae. That means no radar cross-section. At 0 degrees, there's a dual reflection phase seen for AMC Unit 2 at 9 GHz and 18.9 GHz, whereas in AMC Unit 1, a single phase at 12 GHz can be seen. The craziest thing about all of this is that although all simulations were run in the exact same fashion, the values obtained for Unit 2 are not at all equal to those obtained in the research paper that I was using. And that proves that there is so much more scope for making this RCS reduction bandwidth larger and larger. Ultimately, the cell's performances were observed over the same wideband frequency range, 7 GHz to 19 GHz. So these results provide extremely specific foresights into whether similar structures could be assembled as surfaces for solar panels, which is the main goal of this exercise, not creating antennae for military vehicles. How did I transform this into a full-scale metasurface that worked in tandem? Well, 1 month later, and you have this. An adjustable layer that can coat a solar panel using the coplanar loading method. And this can enhance the panel's gain factor almost by 6-fold. It uses the same philosophy that the individual substrates were built on, the idea of a graded refractive index. Light pours onto these small nanostructures which have peaks and cavities that, when arranged in a systematic fashion, reduce the speed of light gradually instead of abruptly between two mediums. Arranging them in a 3x3 orientation, either at 90 or 45 degrees, you obtain 3 different instances where the phase gap equals 0 degrees. That is one of the widest bandwidths you can get. What do we call this structure though? Well, it looks like a chessboard, so it isn't surprising that it's called a chessboard-loaded metasurface, or a CLMS for short. The next stage of my project involves actually understanding the effects of this metasurface, such as bore-side gain and permittivity. Some of these ideas can be easily explained if I just went on the internet, but they actually have so many more applications and details to them. Hopefully, I can use the loaded metamaterial strategy that I've learned about through this project so far to layer a real-life solar panel with these nanostructures. This creates tailored resonance, and it also creates a tandem solar anti-reflection coating that could revolutionize solar technology for decades.